Hi, my name is Danielle Huser, and this video is going to cover the concept of Lagrange points, which fall under a sect of astrophysics called celestial mechanics, which involve the forces that celestial bodies such as stars and planets exert on other objects in space. Lagrange points, by definition, are positions in which the gravitational forces of a two-body system cancel, producing a stable point in which objects can maintain their position relative to the two larger bodies. These points are extremely useful in the astronomical community as they're ideal for housing tools of observation and discovery in deep space. In the Sun-Earth system, there are 5 Lagrange points, referred to as L1 through 5, as shown in the diagram. L1 is currently home to the SOHO satellite, which lies between the Sun and the Earth and revolves during the same period as the Earth. L2 is positioned on the exact opposite side of the Earth, eclipsing the Sun at all times, as it also revolves at the earthly period of 365 days. L3 is located on the side of the Sun opposite to the Earth and is similar to L2 in that the gravitational forces from the Sun and the Earth are canceled by the centrifugal force of the revolving system. These 3 points are considered unstable, as the equilibrium point has a very small area, and an object at this point can easily be pulled from balance and lost to an overwhelming gravitational or centrifugal pull force. L4 and L5, however, are considered stable because they're located at the vertex of an equilateral triangle formed by the Sun and the Earth. Because there are forces pulling in many directions as opposed to 2, they are far less volatile than points 1 through 3. However, due to their considerable distance from any launch site on Earth, astrophysicists typically rely on L1 and L2 for the placement of satellites, or in one case, a massive space telescope. In current events, L2 has become increasingly relevant to the scientific community as the James Webb Space Telescope, anticipated to launch in 2021, will be positioned at L2. Logistically, this is ideal because it provides us with a vast, uninterrupted view of outer space, and the Earth would act as a shield from the Sun's rays, which would interfere with the equipment and image quality. This launch will be extremely risky as the unmanned assembly procedure must occur without a hitch on its journey to L2. As seen here, this complex process begins with the deployment of the sun shields, which will prevent any stray light from detracting from the images and expand to the size of a tennis court. Each layer of the sunshield is thinner than a human hair. The cord-fold wings complete the major aspects of the largest telescope in outer space, and at this point will have cooled to nearly cryogenic temperatures. After any trajectory corrections, the telescope completes the 160-day journey and reaches its final position at L2, where it will revolve alongside the Earth for decades to come. There are currently 5 probes inhabiting Sun-Earth Lagrange points and another 5 in the Earth-Moon system, and dozens proposed to be launched to these balance points in the future. These images shown here are from the Hubble Space Telescope, which is currently the best we have. The Webb telescope will not only be better equipped and overall more capable than the Hubble, but it will also be capable of observing a drastically larger patch of sky, which may lead us to discoveries we could have never dreamed of, and this is possible due to its strategic position at L2. This shows the importance of Lagrange points in the Sun-Earth system and how we can use their applications to our advantage, broadening the horizons of astronomical discovery for generations to come. Thank you.